Morning everyone. So in today's class we'll discuss the problems based on current, conductors, boundary conditions, Poisson's and Laplace equation. So we'll see what are the possible problems that are expected in this module, right? So this is the first problem. So here, please read the question. Find the total current in outward direction from a cube of 1 meter with one corner at the origin and the edges parallel to the coordinate axis if j vector is 2x square ax cap. I think this is plus 2xy cube ay cap and plus 2xy az cap ampere per meter square. So this is the unit for current density j, right? So what we have to find, they have given the cube of 1 meter what to say 1 meter length on all the sides. Cube will have the length same on all the sides with one corner at the origin and the edges parallel to the coordinate axis if j is equal to 2x square ax cap plus 2xy cube ay cap plus 2xy az cap ampere per meter square. So first we'll understand the diagram. So this is what I've told. So this is x, this is y, and this is z, right? So now here the cube is placed in this way. One of the side is in the origin. So this is how the diagram will be. So there's a cube of 1 meter. So here this length is 1 meter. All the sides it is 1 meter, right? And the corner is placed in the origin here, right? So now we have to calculate, the j vector is given, so we have to calculate what is the current coming out of this surface. What is the current coming out of this surface, right? So since it has ax, ay, az, all the coordinates, so it will have current on all the three directions, right? It will have all current on all the three directions. So this is what we have to calculate. So now coming to the basic definition of current density. Current density is given by j is equal to, or j vector is equal to I into S, that is surface, right? So if you take current per surface area divided by S. So now if I want I, then it will be J into S. So forget about this vector here. Now if there is a differential current, then it will be Di is equal to J vector into ds vector, j vector dot ds vector. Now How will we get I? I will be equal to, for a closed surface, it will be j vector dot ds vector. J vector dot ds vector. Now can you see here that this formula is same as Gauss law, where we had d is equal to closed integral, q is equal to closed integral of d vector dot ds vector. It is the same formula. So we can use divergence theorem here. So that is what is written here. So this j dot ds vector over a closed surface integral can be written as volume integral of divergence of j vector into dv. Divergence of j vector into dv. So now here we have to calculate what is the current, and this is the formula what we are going to use. This is the formula what we are going to use. Now already j vector is given in the question, and dv we should know from Cartesian coordinate system. What is dv for Cartesian coordinate system? dv is equal to dx dy and dz. Right? This is dv for Cartesian coordinate system. Now for first we have to find. I'll just erase this one. Yeah. So first we need to find divergence of j vector. So divergence of j vector in Cartesian coordinate system is given by this one, right? So now dou by dou x of jx, dou by dou y of jy plus dou by dou z of jz, right? Now this is jx, whatever is there with ax cap, and here we have one plus sign which is not printed, and here this will be jy and this will be jz. So just substitute in the formula, so you will get this one. So when you solve this one, dou by dou x of 2x square will be 2 will be constant, x square will be 2x, so 2 into 2 will be 4, so it will be 4x. So here 2x is constant, y cube if you differentiate with respect to y, you will get 3y square. So 3 into 2 is 6, so 6x square. And here you can see that in the last term we don't have anything with respect to z, so it will be 0. So the divergence of j vector will be 4x plus 6xy square. So this is divergence of j vector. Now current I, that is this formula we have applied here, that is divergence formula, this formula, right? Now I is equal to, what is this one? This one is nothing but divergence of j vector, and this is dv in Cartesian coordinate system. So divergence of j vector and dv is substituted here with respect to the volume. So since we have dx, dy and dz, we need to integrate it thrice. So first integration, second integration and third integration. So divergence of j vector into dv over 3 integrations. So we know that the cube was placed, one corner was placed at the origin, so all other what to say, edges were parallel to the coordinates. So z should vary from 0 to 1, y should vary from 0 to 1, and x should vary from 0 to 1. So if they have given the limits in the problem, then you have to substitute the limits accordingly. Since here the origin, the edge is at the origin, so we are substituting like this, right? So now integrating only with respect to x, right? Integrating only with respect to x, we get, substituting only with respect to x, we get this one. So when you solve the integration, this is what you get. Now with respect to y and z, this is with respect to y and this is with respect to z. I hope everyone knows the integration. Just take some time and solve this problem. So you should get the answer as 3 amperes. You should get the answer as 3 amperes. So this is one kind of the problem. Here we have discussed only about Cartesian coordinate system. So any coordinate system, if it is asked, so you should be knowing that. So what all things you have to know here is, we need to know how to calculate the divergence of j vector for the given coordinate system, and we need to know what is dv for the respective coordinate system. So if you know these two, and if you know how to solve the integration, you will be able to solve this kind of problems, right? So where j vector is given and you are asked to calculate what is the current, what is the current flowing through the surface, right? So this is one kind of the problem. We'll move on to the next problem. Hmm, yes. So just read this problem. A wire of diameter, a wire of diameter 2 mm, 2 mm and conductivity of 5 into 10 to the power 7 mho per meter. Mho per meter. So this is the opposite of resistivity. This is conductivity. So 5 into 10 to the power 7 mho. This is not ohm. This is mho per meter. Has 10 to the power 29 free electrons. So number of electrons is 10 to the power 29 per meter cube. Per meter cube. This is subjected to an electric field of 10 millivolt per meter. 10 millivolt per meter. Determine the first thing. We have to calculate what is the free electron charge density. We have to calculate what is the free electron charge density. Then we have to calculate what is the current density. We have to calculate what is current density, and we have to calculate what is the current in the wire. What is the current in the wire, and we have to calculate what is the drift velocity. So these kind of problems are important because you can get an idea about all these four, right, in a single problem. So please note down the formulas properly here, right? So the first one is simple. You have to calculate what is the total number of electrons. I mean, sorry, we have to calculate what is the free electron charge density. We have to calculate what is free electron charge density. It is nothing but number of electrons into the charge on electron. Now here, that this is given in the question itself here, that is the charge on electron is minus 1 to the 1.6 into 10 to the power minus 19 coulomb. So even if this is not given, you should know this value. You should know this value, right? Here it is given, so no problem. If it is not given, then you should note the value of E, right? So now we have to calculate what is the what is the free electron charge density. So it is given by N into E, N into E, where N is number of electrons, where E is charge on each electron. So when you multiply those two, there are 10 to the power 29 electrons, and this is the charge on each electron. So this is what you get, that is coulomb per meter cube. So this is nothing but rho V, correct? Rho V. Now next one, you have to calculate what is current density. Current density is given by sigma E, Ohm's law. We have discussed in the previous lecture, right? Previous to previous lecture, that is J is equal to sigma E. Sigma is given, that is conductivity 5 into 10 to the power 7 mho, that is this one, right? And E is also given, that is it is 10 to the power, sorry, 10 millivolt per meter. So just multiply those two, you will get this one, that is 500 kilo ampere per meter square. Now we have to calculate what is the current. So current calculation is simple. We have the definition of J as I by S, current per surface area. So we have to calculate the current, and we know what is the current density. So cross multiply that one, it will be J into S, J into S. So it will be J into, how did we get this one? Pi by 4 d square. So it is a wire. Wire is nothing but, it will be circular. It will be in circular shape, and diameter is given as 2. So what will be the surface area? It will be pi r square. Since we have diameter, how to substitute for r? R will be d by 2. So d by 2 the whole square will be d square by 4. So pi by 4 d square. So we know what is the diameter and we know what is J. So this is the current what is flowing through the wire, right? Next one, we have to calculate what is the drift velocity. So this is the relation between what to say charge density and drift velocity. We have discussed this when we discussed uh, when we derived the equation for convection current. So J is equal to density into velocity. So drift velocity will be current density divided by the charge density. So the drift velocity will be minus 3.125 into 10 to the power minus 15 meters per second. So why we have negative sign here? The negative sign indicates it is opposite to the direction of the applied electric field E. It is opposite to the direction of applied electric field E. Always the electron movements will be in the opposite direction, right? So these are the formulas which you have to note. We have already discussed in the previous class, but while solving the problems, if you note down the formulas, it will be easy for you. So this is the this is the equation for charge density, that is number of electrons into charge on each electron, and this is the equation for current density, that is Ohm's law, sigma into E. This is, that is current density formula, and this one we have derived in convection current. For calculating this VD, we are using it here, right? So these are the four formulas which you can note down here, right? Which may be useful for solving other problems. So we'll go to the next problem. So this is a problem based on boundary conditions, right? So the region with Z less than 0 is characterized by epsilon R2 as 2 and for Z greater than 0 by epsilon R1 is equal to 5, right? If D1 is equal to 2ax cap plus 5ay cap minus 3az cap nanocoulomb per meter square, find d2 vector, dn2 vector, d tan 2 vector. This is not required here. Energy density we'll see. Angle through d2, angle angle that d2 makes with z axis, d2 by d1 and p2 by p1, right? So now here what they have given is, how do we differentiate z? So when you have Cartesian coordinate system like this, right? So this is z less than 0 and this is z greater than 0, correct? So whatever region we have from this point upwards is epsilon r1. So here it is epsilon r1 and here it is epsilon r2, right? So this will be the boundary. So this will be the boundary, that is z is equal to 0, z is less than 0 and z is greater than 0. So when z is greater than 0, it is epsilon r1. When z is less than 0, it is epsilon r2, right? So on this boundary we have to calculate what is d2, what is dn2, what is d tan 2 and energy density and all those whatever they have asked, right? So first you need to understand this one. So they've specified the boundary. Here the boundary is the boundary plane is xy axis. So this is x, y and z, right? Now they've given what is d1. We have to calculate what is d2. So d1 is given. Now from the formula when we derive the equation, we know that whatever is tangential, this is tangential component, and this is normal component. So always this is normal component and this is tangential component. So always these two will be perpendicular, right? Always these two will be perpendicular. Now if I take the same example like this, yes. If I take the same example like this, now this is the boundary, this is the boundary. Now if I take this as normal and this as tangential, right? So always this normal part will be along z-axis. This tangential part can be anything. This tangential can be anything. That is, it will be a mixture of both x and y. It will be a combination of both x and y. Here you may see that it is exactly along y-axis. So it is not only y. It can have x-axis also, x-axis component also. Right? This will be useful when we are solving the what to say normal and tangential components. Now with this knowledge, yes. Now d1 is given here. D1, this is from the question. D1 is equal to 2ax cap plus 5ay minus 3az nanocoulomb per meter square. Now D1 will decompose into two parts, as I told you, normal and tangential, right? Now Dn1 will be equal to minus 3az, as I told you. Tangential normal part will always be perpendicular. So perpendicular to xy plane will be z-axis, right? So 3az cap minus 3az cap. This is normal. Tangential part will be whatever is remaining from after subtracting the normal part. So d minus dn1. So that will be the remaining part. That is this one. 2ax cap plus 5ay cap. 2ax cap plus 5ay cap nanocoulomb per meter square, right? Now according to boundary conditions, dn1 and dn2 both are same. dn1 and dn2 both are same. So it will be minus 3az cap itself. So we got what is dn2 here. We have found what is dn2. So dn2 is nothing but minus 3az cap. Now we'll go to the next one. Yes. Now we have to find what is d tan. We have to find what is d tan 2. So this is the formula what we derived in the derivation when we discussed boundary conditions between two dielectrics. So d tan 1 is this one which we did in the previous slide. D tan 2 we have to determine, and 5 by 2 we know what is epsilon r1 and epsilon r2. We are just substituting those two what to say numbers here. So d tan 2 cross multiplying this, we get this equation. So d tan 2 is given by this equation, 0.8 ax cap plus 2ay cap nanocoulomb per meter square. Now again d2 will be having both normal and tangential components. So this tangential component I'm adding here, and we obtained that this dn1 and dn2 is same in the previous slide. dn1 and dn2 both are same, that is minus 3az cap. So that minus 3az cap is coming here. So this is nanocoulomb per meter square. Now they have asked d2 here, that is the first part. So we have obtained that also. We have obtained that also. That is d2. Now energy density is given by 1 by 2 d1 square by epsilon 1. This was derived in the second module if you remember. You can just go through that video or slides. So it will be half of d1 by d1 vector square divided by epsilon naught epsilon r1. So here this is epsilon 1. So you have to include both epsilon naught and epsilon r. right? So substituting in that formula, you get the energy density as 0.4291 microjoules per meter cube, right? So this is how we solve that. Now, does it that is WE1, that is due to epsilon 1. Now due to epsilon 2 we have to calculate, that is D2, same formula where we are substituting it as D2. So here we get 0.3851 microjoules per meter cube. So to find the angle of D2 with Z axis, that is minus AZ cap, is to be obtained by the dot product. So D2 dot minus AZ is equal to, this is the definition, this is from the definition of dot product, right? So when you solve this one, cos theta 2, so you get theta 2 as 35.678 degrees. Why did we do this here? D2 dot minus AZ cap, because this was the quadrant which we had taken. So this was the plane which we had taken, right? Boundary. So above it was D1, below it was D2. Now they're asking us to calculate what is the angle done with respect to D2 with and Z axis. Now D2 is along minus AZ, right? And D2 is below that. So that is why we need to find D2 vector dot minus AZ cap. AZ cap. So then we'll know what is the angle. Now AZ is exactly with respect to Z axis. Now we'll know what is the angle made with respect to this Z axis. That is why we are finding the dot product of these two. So A2 dot AZ cos theta 2. So you will know what is cos theta 2 from this. Now alternatively, tan theta 2 is equal to tan theta 2 d tan 2 by dn2. So you will get what is theta 2 here. This is one more formula for calculating it. You can use any one method, right? So next one, d2 by d1. So what is the ratio? d2 vector by d1 vector. So it is 0.599, 0.599, because that was also asked here. D2 by d1. You can ignore this one. This is not there. Calculation of power. This requires some other formulas which is not there in our syllabus. So you can leave that. So d2 by d1. Calculated this. So just you should know what is the outline of the boundary condition equations, right? So we need only these formulas here. What is d1 vector? What is d2 vector? And you should know that dn1 and dn2 are equal in boundary condition between two dielectrics. From that we'll be solving the problem, right? You should know only the formulas and the flow of the problem, how to solve. Yes. Now next problem. Determine whether or not the following potential fields satisfy Laplace equation. Now there are three problems here. They have given V everywhere. V is given, correct? You can see that V is given. V, and V. What you have to observe here is it is given in three different coordinate systems. This is Cartesian, this is cylindrical, and this is spherical. Now we have to check whether this particular field satisfy Laplace equation or not. So for that what you have to do is, anyway V is given, so you have to find what is del square V. What is del square V? And if the answer is 0, this particular field V satisfies Laplace equation. And if del square V, if you get some equation or some number which means that it is not equal to 0, then this V doesn't satisfy Laplace equation. This equation doesn't satisfy Laplace equation. Now, Cartesian, cylindrical or spherical coordinates respectively is given by this formulas you have to note down. Anyway, we had discussed this in the previous lecture, right? So these formulas you have to note down. Now you have to apply this formula for Cartesian, and you have to apply this formula for cylindrical, and you have to apply this formula for spherical, right? Solve these. You know how to solve dou square V by dou x square, right? You can solve this one, and then you have to check whether the equation is equal to 0 when you solve this. If it is equal to 0, that means that it satisfies Laplace equation. If it doesn't satisfy, then it doesn't satisfy Laplace equation, right? And one more important thing what you have to note here is determine whether the following potential fields satisfy Laplace equation or not. Here they have given directly to verify whether it satisfies Laplace equation or not. In some of the questions they'll give you the same questions and ask you to determine whether the given fields are of free of charge. That means rho v should be equal to 0, rho v equal to 0. So in Laplace equation rho v is equal to 0, that is why we get del square v is equal to 0. So both cases you have to check for Laplace equation itself, right? So if del square v is equal to 0, which means that it is free of charge, right? So I hope everyone will be able to solve these three problems. I'm not going to show the answers, or I'm not going to solve these problems here. So you should know how to solve that. Yes. So if you remember this problem or this derivation we had done in the previous lecture, we had solved this using Laplace equation, and this is a spherical capacitor here. There we had done with respect to A and B, and here we are doing it with respect to some numbers. So here R is given, R for the first case, that is A is equal to zero point 0.1 and R is equal to zero point 0.2 for B, and in here it is opposite side. In the derivation what we solved, this was V naught and this was grounded. Actually this was grounded, the outer cylinder was grounded, but here they have given in the opposite side, that is V is equal to 100 for the outer cylinder, and the inner cylinder is grounded, and we know what is the radius of both, right? The outer cylinder and the inner cylinder. Now we will start with Laplace equation. So we know that we have to start with Laplace equation. So now Laplace equation, it will have only radial part. We have discussed this in the previous lecture. So here it doesn't depend on theta and phi. It doesn't depend on theta and phi. So it depends only on our radial component. So only R equation is taken from the equation. That is, if you refer this equation, we have taken only this part, and we have not considered these two parts because it doesn't depend on theta or phi, right? The same equation is written here. So when you cross multiply this r square, it will become 0, so you'll get only this part is equal to 0. Now if I want to remove this integration, I have to integrate on both the sides. If I integrate on both the sides, this r will go off, so r square dou v by dou r is equal to integration of 0 plus c1, which is equal to c1 itself, because this integration of 0 will be 0, right? So next here this will be dou v. So dou v by dou r is equal to c1 by this r square is brought down here. So c1 by r square. Now next, integrating v again, because we have dou v by dou r here. So integrating it again, we'll get one more constant here. So integration of c1 by r square dr plus c2, which is equal to minus c1 by r plus c2. That is, integration of 1 by r square with respect to r will give you minus 1 by r, and this c2 will be as it is. Now at r is equal to 1 meter, zero point 0.1 meter, V is equal to 0, and when R is equal to 0.2 meter, V is equal to 100. So we are going to substitute these conditions here. That is, when I substitute R as zero point 0.1, I have to substitute V as 0. When I substitute R as B, that is zero point 0.2, I have to substitute V as 100. When you do that, you will get these two equations. You will get these two equations, right? So when you subtract these two equations, that is, you take this as equation 1, you take this as equation 1, and this as equation 2, right? So 1 minus 2 gives you this one, Now after solving that, you will get what is, I mean, here they have substituted for C2. What is C2 here? C2 here in this equation, what is C2? C2 is equal to C1 by zero point 0.1. So in this equation, consider this equation here. 100 is there, it's 100. I mean, after subtracting, we got minus 100 is equal to minus C1 by zero point 0.1 minus of minus C1 by zero point 0.2. When you solve this, you will get it. So minus 100 is equal to minus 10 C1. 1 by zero point 0.1 is 10 C1 plus 1 by zero point 0.2 is 5. Minus into minus plus 5 C1. That is C1 is equal to 20. So we got what is C1. Next we have to find what is C2. So C2 will be obviously 200 from this equation. So C2 we got it as 200. So we got C1 and C2. Now what I'll do is I'll substitute C1 and C2 in this equation. Which equation? In this equation. So minus C1 by R plus C2. So V is equal to minus 20 by R plus 200. Now we've got what is V. So this is one part of the problem. Now second part, we have to find what is V. Sorry, what is E vector. E vector, we know that it is negative gradient of V, and again we'll have only AR part. So this negative gradient of V, you have to refer the formula from the second module. So then when you solve that, you'll get what is E vector, that is minus 20 by R square AR cap volt per meter. We got what is E vector. And how to calculate D vector? D vector is nothing but epsilon naught into E. So when you solve that, you will get what is D vector also, right? So that is what is asked here. So find what is E vector and D vector using spherical coordinate system. So we have found that. First we have to find what is C1, C2, C1, C2. Then when you find C1 and C2, we'll get V. So from this, we'll get what is E vector, and we'll get what is D vector. So this is how you solve this problem, right? So we'll move on to the next problem. Yes. So here the same problem what I discussed in Laplace equation. If the if the no, this is different. If the field of a region in space is given by E vector is given, they have given you E vector. Is the region free of charge? Yes, correct. We have to check whether it satisfies Laplace equation. Now here V is not given directly. Now if you consider these problems, V was given directly and you are asked to find whether it satisfies Laplace equation or whether the given field is free of charge. But here they have given you E vector, but E vector cannot be used directly. So first we have to find what is V, right? What is V we have to find. So E vector is gradient of V. Yes, this E vector is minus gradient of V. So E vector is known. So that is minus gradient of V. So gradient of V will be minus, will go to the other side. We get this equation. Now we need to know what is del square V. So del square V, again I'll find the dot product of del operator and this gradient of V. So del dot, this equation will give you, this is the equation for del, and this is the equation for gradient of V. So when you solve those two, We'll get only this equation because this equation has only az cap. So this and this will not be required. So when you solve that one, you will get del square v is equal to minus 5 minus sin z is equal to 5 sin z, which is not equal to 0. Which is not equal to 0. Hence, the given region is not satisfying Laplace equation. Hence, rho v is not equal to 0. So, there are some charges which is present in this region. Hence, the region is not free of charge. Hence, the region is not free of charge. Right? So, we'll revise the problems once more, whatever we have solved today. So, this is the first problem where they had given j vector and you have to calculate I vector, current I. So, you have to use this formula here. This is same as our Gauss law, and this too is same. This is from divergence theorem. So you can use either this or this. Both will give you the same answer. The problem with this is you have to solve this particular equation for 6 planes. For 6 planes you have to solve because there are 6 planes in the cube. Whereas here this is only one volume, dx dy dz, and find the divergence and solve. So this is the easiest part. But if they ask you to verify both the sides of this this equation, then you have to solve this as well as this, right? And you have to show that the answer will be the same, right? So here we got the answer as 3 amperes. And this is one more where you have to calculate the electric field, charge density, current density, current and drift velocity. So you have noted all the formulas. This is just the direct substitution to get the answers. And this is based on the boundary conditions, right? And here you should know that the tangential, the normal part will have az component, and the tangential part will have x and y, both x and y components. So all these are from the formulas of boundary conditions, so which you have to refer, right? Then you will be able to get the answers whatever they've asked. So they've asked for d2, dn2. First we'll find what is dn1. So dn1 and dn2 will be same. So we'll get this one first, and then d2 we'll get here. D2 will be getting using this formula, and we got what is d tan2 also, and we got what is the angles also, right? And I've explained you why we have taken this d2 dot minus az, and we got both the angles. So now we got what is the ratio of d1 by d2, right? So here you have to find what is, I have not solved this problem here. So you have to check whether the given region is free of charge, or you have to check whether it satisfies Laplace equation. So you have to find what is del square V. If del square V is equal to 0, it satisfies Laplace equation. If del square V is not equal to 0, then it means that it doesn't satisfy Laplace equation, right? Same thing for all the three. So here, this is Cartesian coordinate system, this is cylindrical, and this is spherical. So you should note the formulas accordingly. So this is for Cartesian, this is for cylindrical, and this is for spherical. So apply these formulas and try to check whether they are they satisfy Laplace equation or not. So this is the same thing what we derived in the previous class, previous class. Previous class. So here you have we had solved actually how to find capacitance using Laplace equation. So the same thing we are doing it here. So here first we have to find what is C1, C2, you know that one, and from C1 and C2 we'll get what is V. From that we have to calculate what is E vector and what is D vector. You can take one problem as a homework. So what you try to do is you just interchange these voltages. Instead of taking this as 100, you take this as 0, and you take this as 100 and try to check what will be the difference, right? So what I'm trying to tell is you take this as grounded and you take this as 100. right? This has 100 volts. Please try to solve this problem and send it to my WhatsApp. I'll just check whether it is correct or not, right? Only thing is the equation will change here. The equation will change here. The values of C1 and C2 will change. If C1 and C2 will change, E vector will change and D vector also will change. Try to do that, what to say, and try to interchange the voltages and try to solve that problem just for your understanding, right? So next problem was, there was a field which was given, electric field, and you have to check whether the given field is free of charge. So you have to find what is del square V. If del square V is not equal to 0, that means that there are some charges which is present. So rho V is not equal to 0. Rho V is not equal to 0. So if rho V is not equal to 0, it means that del square V is not equal to 0. Del square V is not equal to 0. Hence, it doesn't satisfy Laplace equation, or the given region is free of charge, right? So that's all for today. So we have solved some problems in this module. Try to go through these problems and try to solve the problems by yourself, right? Please try to solve the problems by yourself. From the next class, we'll start with the fourth module, magnetostatics, right? Thank you.